Hello everyone, today let's solve the problem number 338, counting bits. So what the question states here, we have been given an integer n. You can clearly see here, we have been given an integer n, return an array ans. So we have to return an array answer of length n plus 1. We have to return an array of array answer ans of length n plus 1, right, where ans of I, answer of I, is the number of ones in the binary representation of I. So ans here in this case, answer of I, iterated value of the answer, or ans, is the number of ones in the binary representation of I, right? So simple. Constraints we have been given here, 1 less than or equal to n less than or equal to 10 to the power of 5. This is fine. What is our main goal here in this case? This one constraint I was speaking of. So the goal is to solve this in big of n time. So we have to solve this one in big of n time without using any built-in bit counting methods. So built-in bit counting methods, we shouldn't use any built-in bit counting methods, right? So this is fine. So first thing, let's come to the first example here. So I'll just come here. In this case, we have n equals to 2. So in the binary representation of 0, 1 and 2, we will go. So means n equals 2 means we will consider 0, 1, 2. N equals 5 means we will consider 0, 1, 2, 0, 1, 2, 3, 4 and finally 5. So this thing. So when this one is 0, n equals 0, means the binary representation of 0 is 0. So 0, 0 ones we have. In this case, the binary representation of 1 is 1. So we have 1 1 here. Binary representation of 2 here is 1 0. So we have 1 1 here. So we will represent this one 1. So the output that we need to return here is 0 1 1. This is fine. I hope this is clear. Easy, simple, right? So let's go with the second example here. So just give me a second here. So yeah, let's go with the second example here. We have 0 1 2 3 4 and 5. So the binary representation of 0 is 0. The binary representation of 1 is 1. The binary representation of 2 is 1 0. So 1 we have 1 1 here. So we'll return the count as 1. So binary representation of 3 is 1 1. We have 2 ones here. So we will go with 2 here. So the binary representation of 4 is 1 0 0, and we have only 1 here in this case, 1 1 in this case. The count of 1 is 1. So we'll go with 1. So in this case, the binary representation of 5 is 1 0 1. We have 2 ones here, so the count will be 2. So the output that we need to return here is 0 1 1 2. So in 4 we have only 1 1, right? So this one has to be 1. Sorry, not 2. So this one has to be 0 1 1 2 1 2. See here, 0 1 1 2 1 2. This is fine. So this is the output that we need to return. Simple, right? Simple to understand. They have given us wonderful examples just for the sake of understanding, right? So here I hope the question is completely clear. What we need to do is completely clear as well. First, let's discuss the approach, followed by the edge cases one by one, and then finally write the code and discuss the complexities for the code that we have written. Initially, let's discuss the approach first. So the first thing that we need to note down here is we'll be making use of dynamic programming, or we'll be going with the dynamic programming with bit manipulation approach. So just keep this in mind, DP with the bit manipulation approach. So n equals to 2, we have already seen how we got this output. So basically 0 1 2, we'll be considering n means n equals 2 means we have to consider all the numbers from 0 to n, right? 0 1 2. So here in this case 0 binary representation 0 1 1 2 1 0. So we have 0 ones here, we have 1 1 here, so we have 1 1 here in this case, right? So we have to go with the output 0 1 1. We have already discussed this one. Let's go with the step-by-step execution. N equals to the same example I have considered here, the first example, right? Binary of each number we know 0 0. So count 0, count 1 in this case, count is 1. So this is fine. Let's go with the logic. Basically, for any number I, we can get the count of ones by removing the least significant bit. Just remember this one, by removing the least significant bit we can, right? So for any number I, we can get the count of ones by removing the least significant bit. Using I, we will be making use of the right shift operator. So we can just remove the least significant bit, right? So by making use of the right shift operator, here you can clearly see double right shift operator, right? So adding 1, if the we will add 1 if it is the current bit, right? So I ampersand 1 is 1. We know this one. We are going with the AND operator here, right? I ampersand 1 is 1 in this case, right? So here what we get, answer of 0, quite obviously it is 0. Answer of 1 is, in this case we are going with the DP, nothing but 0 plus 1, it is 1, right? Answer of 0 is nothing but 0. 0 plus 1, this one will give us 1. The answer of 2 is, answer of 1, basically it is 1 plus 0, again it will be 1 itself. So 0 1 1 we got here in this case. So the final output that we got here is quite obviously 0 1 1, which is equivalent to the output that they have given for the example 1 in the question, right? So the approach works absolutely correct in this case. As we are completely familiar with the approach, let's discuss the edge cases one by one. So here we have when n equals 0, so output is quite obviously 0. When n is 0, quite obviously output is 0, because binary representation of 0 is 0. We don't have ones, we will return 0. In this case, when n equals 1, we have 0 comma 1. Binary representation of 0 is 0, binary representation of 1 is 1, so we have only 1, right? For the 1 we have 1 1, and for the 0 we have 0 1. So 0 comma 1 will be the output in this case. This one I am speaking of. So for this one, let's consider n equals 10 to the power of 5. Output will be valid array of the size 1 0 0 0, 1 4 zeros and 1, this one, right? So it should be of the valid array of size 1 0 0 0 0 1, we can say. So this has to be efficient on big of n time and big of n space, right? Why it has to be efficient on big of 1 and big of n time complexity and the space complexity here? Because we are making use of the DP, and here the time complexity and the space complexity would be quite obviously big of n, and this one big of n. For the time complexity big of n, and the space complexity is big of n in the worst case. We know this one, right? So it shouldn't cause any, basically it shouldn't cause any overflow or MLE. MLE means memory limit exceeded, right? So it shouldn't cause any overflow or the MLE. So in this case, whatever the code that we write should contain this one, valid size of array, valid array of size, this one 1 0 0 0 0 1. So these are the 3 edge cases that we need to consider. This we need to keep in mind. So now we are completely familiar with the edge cases as well as the approach. As we are completely familiar with the edge cases and approach, we are good to write the code. Let's start writing the code. So what we'll do here, we will create the result array of size n plus 1 to store the bit counts. We have already discussed this one, right? So here on this case, I'll just write, sorry, let me give here int answer result, this one result variable, I'll just consider answer ans here. In this case, new int of size n plus 1, right? I'll just give here n plus 1. So this is fine. So the next step is we will iterate from 1 to n. So let me quickly write the for loop here. N I equals 1. So what did I write? 1 I less than or equal to n I s plus. This is fine. Within the for loop, what we will do, so we'll be making use of the right shift operator, double right shift operator. We have already discussed this one. I double shift operator, double right shift operator 1, nothing but we are dividing by 2. So see here, I'll just write this one out so it will not be confusing. So I right shift 1, nothing but we are dividing this one by 2. We are removing the last bit, means we are reusing the result of the smaller number. So this is equivalent to the I by 2, right? So I'll just be making use of the, we are going with a bit manipulation, so we are making use of double right shift operator in this case. Also we will be making use of the I ampersand 1. We are performing the this one AND operation here, right? I ampersand 1, nothing but we are checking if the current number is odd. If it is odd, then we have to add 1, or it adds 1 if the last bit is 1. So we are going with the I right shift operator 1, nothing but dividing by 2, and I ampersand 1. I hope this is clear. No confusion, right? So within the for loop, what we will do here in this case, answer of I, iterated value of the answer equals answer of, here in this case, I double right shift operator plus I ampersand 1. This is fine. So the final step here is what we will do. So we have to return the answer, right? So what did I do here? Just give me a second here. Yeah, this is fine. So the final step is we have to return the final result array. So in our case, the variable we have considered ans, right? So I'll just return ans here, answer variable. So let me hit the run button. So I hope this works. Let's see. So let me enlarge this one. Yeah, you can clearly see here the sample test cases are getting passed. Means the code works absolutely correct on this case. Let's see whether this works for all the test cases or not. I have hit the submit button. Let's see. So here you can clearly see all the test cases are getting passed. Means the code works absolutely correct on this case, right? So let's quickly discuss the complexities for the code that we have written. So the approach that we went with here is dynamic programming with bit manipulation. We know this one, right? The approach that we went with here is dynamic programming with bit manipulation. So the overall time complexity, we have already discussed this one. Overall time complexity is because we are computing the result for each number from 1 to n. See here, this one I'm speaking of for loop. So you can just go for the for loop here, right? So we are just computing the result for each number from 1 to n once using the constant time operation. So will be the time complexity will be big of n in this case. So what would be the space complexity here? The space complexity would be big of n as well. Why? Because we are making use of the integer array answer here. This one I'm speaking of, right? We are making use of the integer array answer, which is of the size n plus 1 to store the answers, right? So the space complexity would be big of n in the worst case, right? It will be big of n. So the time complexity and the space complexity for the code that we have written is big of n in this case, right? So I hope the complexities are completely clear, and I hope whatever the code that we have written is completely clear as well. For now, this is it. Thanks for watching, guys.